So this problem is your classic application of Pascal's principle. Remember, Pascal's principle is the idea that when you apply a force or a pressure to one part of a fluid, that pressure is translated equally everywhere throughout the fluid. So here we have this hydraulic lift. So these hydraulic lifts are used to lift cars, but another example of it is a bike pump, right? When you pump up the air using a hand pump, you can pump up a car tire with that, and you can actually lift a car quite easily with a hand pump. So this is just an application of that idea. So we have this hydraulic lift, and we want to lift up this car here, right? So there's some little car that I didn't draw. There's a little car here, and it exerts the weirdest looking car ever. Anyway, but it exerts some force down, right? We're going to call F2. And we're capable of exerting some force, F1. So what we want to figure out is the ratio of these areas, of these pistons here, that will allow us to apply some force F1 and lift the car, force F2. What Pascal's principle says is when I push down with F1 and I make some pressure that is, some delta P1, which is equal to F1 over A1, well, that's equal to the change in pressure at piston 2, which is equal to F2 over A2. And so we have this ratio, which we can easily solve for. So we can just manipulate this a bit to get this in terms of F1 over F2 is equal to A1 over A2. And we're told in the problem that we can exert 500 newtons. The car weighs 10,000 newtons. And this ratio is 1 over 20. What we find out is that A2 has to be 20 times bigger than A1 to lift the car, or to hold the car stationary. Hold the car stationary. So I just want to think about this for a little bit, because at first glance it looks like there might be a bit of magic happening here, right? We're pushing down with some force, and we're able to generate a much larger force by doing it. And so if I were to actually lift this car, aren't I getting something for free? It almost seems like, this is violating the conservation of energy. And I want to show you that this isn't violating the conservation of energy. And the reason is because the fluid that moves when I push down, let's say this piston down here, right? So I push this piston down, and there's some amount of fluid that has been displaced. Well, I know that the volume of the fluid has to be conserved. So this is the continuity equation. And what I see is because this piston is much bigger over here, the amount of fluid that gets, the height of fluid that gets pushed up on this side is much, much less, right? So the thing to note is that this volume of fluid is equal to this volume of fluid. And we're gonna use this to investigate the rest of this. So we're asked, how far do we have to push down on this side, H on this side, to push up the car on this side by 1 centimeter. That's what we're asked in the problem. So let's work through that. So part B. So I know fluid volume is conserved. So it means that delta V2, right, the height that the amount of volume that it's changed on this side, which is equal to the piston, area of the piston times H2, must be equal to delta V1, the volume on this side, this other side, which is equal to A1 times H1. And now we have an equation we can solve for, right? So we're interested in finding what the height H1 is, which is equal to A2 over A1 times H2. We have A2 over A1 from the first part of our problem, which was 20. And the height that we're interested in lifting it by is 1 centimeter. And so we get 20 centimeters here. Right. So we have to push down way more on one side to lift up just 1 centimeter. So let's look at the work that we do here. Let's look at work or energy, right? What is the work that's done? Well, the work that's done on the one side, right, is F1 times H1. Well, this is a little force times a big distance, right? And this is equal to F2 times H2. Well, this is a big force times a little distance. And so they actually both equal out. So the same amount of energy is used. We get, as a bonus, we get the ability to generate more force given a little force, but we don't get to lift it as much. And this is what we see, right, with the hand pump example, lifting the car. Like, to lift the car even just a little bit, you have to pump that hand pump so many times to inflate that tire just to lift the car, a fraction of a centimeter even. So, all right.